Fisher projections. I mean, not Fisher projections. Newman projections. We did Newman on the previous one. We'll also need to look at chair. Confirmations. Okay, we did the first one. How about the second one? We did not do it, right? Very sterically hindered base. What type of reaction we're going to have here?
E2.
Why E2? Why not SN2? What? It is pretty sterically hindered. Hindered nucleophile / bases are going to prefer elimination. Then with elimination, it's like, okay, which elimination? Which elimination is this going to prefer? Say it's for Hoffman. Hoffman. What's the Hoffman product here? Hoffman product would be removing which beta hydrogen? You got a beta hydrogen here, and you got a beta hydrogen here. HA, HB. Removing HB would give the Hoffman, right? That would be disubstituted. Put double bond here, it would be trisubstituted. Disubstituted, double bond there with a methyl, and boom. 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 Double bond here, this would be your Hoffman product. Yep. Why did I draw a trans? Or should it be cis? This alkene stereogenic. Why not cis? What's the requirement for the H in the leaving group when it eliminates? Anticoplanar. Okay. Up here we had to rotate it a certain way. Here's an important thing. Up here we were eliminating, when we did the rotation, we were looking at this hydrogen. And we were putting the double bond in here, and we had to figure out how the resulting alkene would be, cis or trans, etc. You only need to do that when there's only one beta hydrogen on the carbon. Because that one must be anticoplanar to the leaving group. Down here, there's actually two there. Call it HB and HP prime. Right? They're the same. There's two. Since there's two, you have two choices. You have a choice. Since you have a choice, you're really choosing between your two different alkenes. See, up here you're not choosing between two different alkenes. You only can get one alkene because there's only one hydrogen. And it has to be anticoplanar. Because you have two, you have a choice. And since you have a choice, which is better, cis or trans? Trans. So that H is the one that's going to come, and so I won't go further. But when you have a choice, you're going to get the best alkene, and it's going to be trans. That's why I drew a trans. That's the Hoffman product. Okay. What if you were asked to show the Zaitsev product here? Even though sterically hindered base maybe favors Hoffman, what would the Zaitsev product be? Does anybody have that? That would be removing HA, right? Because that would make triple double bond here, and that would be trisubstituted. There's only one H here. It has to be anticoplanar to the chlorine. Here we're going to have to really look at it closer. Only one H. Let's look at it closer. I'm going to do my Newman standing over here. We're going to eliminate this H. But let's draw it. First carbon, I got a methyl straight down. I'll call that methyl. There's your methyl straight down. Over here, coming towards you guys is the H. HA. And going behind the board is the ethyl group. That's to my left. to my left. Back carbon, I got an alpha going straight down. It's eclipsed with this. Second carbon, I got a chlorine coming towards you guys, to the right. To the right, it's actually eclipsed with that. And then on the second carbon, I got an undrawn H going to the left. I can draw that in. Going to the left, it's actually eclipsed with this. I'm going to draw it to the bottom of it. Okay. As on the board, the H that's being eliminated in the leaving group are not anti-coplanar. They're actually syn-coplanar. They're eclipsing. They're both like this. Here's the plane, there's syn. We need to rotate this H over here. If I turn the front and put the H over here, that's going to give, okay, I'm not turning the back, so the Cl is here, the H is here, and the ethyl is here. Front now, the HA is here. Everything's rotating, what, 180? So that means the ethyl is going to go here. And what else is on the front? A methyl is going to go straight up. Now we can eliminate, because the H in the leaving group are anti-coplanar. And it's only one H. If we had two H's, then we can draw two different conformations which could eliminate. We can only draw one that can eliminate. This is our only choice. And the only choice shows that the ethyl groups are on the same side. And the methyl and the H are on the other side. So when we draw our alkene here, this carbon has an ethyl on it. The alkene's coming in here, right? This carbon has an ethyl. The other carbon has an ethyl and a methyl. But the ethyls are on the same side. The methyl is opposite. So this is your Sate-Seth. Tri-substituted. That's di-substituted. Tri is more stable alkene. It's the Sate-Seth product. It turns out that the ethyls being on the same side, the two bigger groups, this is what? Z. It's actually Z. So we got the Sate-Seth product by an E2, it would be this, Z. This base is going to favor more the Hoffman. It's very sterically hindered. Sterically hindered, making these H's more accessible. Well, this H is buried between these two groups. So Hoffman, Sate-Seth. What would you get if you did this, if this eliminated by an E1 mechanism? Somebody? Sate-Seth, but Sate-Seth has two stereoisomers. E1 gives what?
Most stable. Trans.
E1 gives most stable product possible. That would be what?
Trans.
That would be Sate-Seth E. So E1 would give the E version of the Sate-Seth. Questions about this?
Question. So it is the most stable out of all the products possible, right? I
What?
said, well, the E1 elimination gives the most stable product out of all the products possible, or just out of Sate-Seth?
Or just out of what?
Sate-Seth. I'm asking.
Well, I mean, but the Hoffman is never more stable than the Sate-Seth.
True.
I would look back on the previous page and we can find it over there. next one is a ring here. THF, common solvent. What is TEA? Anybody?
Triethylamine.
Triethylamine. Triethylamine. It's a base. It's a nitrogen base. Strong or weak? Base.
Strong.
We've always called it strong because strongs are anions or sp3 nitrogen. sp3 nitrogen. It's a strong base even though it's neutral. Now, of course, it's not the strongest base around. It's a relatively weak of the strong. We can still classify it as a strong. Since it's strong, it can do E2. And the fact that it's sterically hindered, the lone pair sort of hidden in there between these wings, makes it good for E2, as opposed to it doing substitution. When we looked at amine nucleophiles, we actually said that this base is commonly used for E2 eliminations because it's sterically hindered. Triethylamine. You may also see it written maybe like this. There's a variety of ways to write compounds, right? It's the nitrogen with 3 ethers, triethylamine. So we got this ring compound here. I have a leaving group on a tetrahedral carbon. This sort of implies E2, strong sterically hindered base. What's going to be the product?
Hoffman.
Well, we have a beta hydrogen here, and we have 2 here. B and B prime are the same. Somebody said something?
Hoffman.
You're going to give Hoffman. Why Hoffman?
Because it's hindered.
We have to kind of clarify this. It's never going to mess you up on a test, but some instructors say, hey, it's not going to be substitution, it's going to be elimination because it's hindered. Well, elimination is going to give the Zaitsev his favorite elimination. And Zaitsev would be removing which H?
The bottom.
That one. The double bond here. This would be on the double bond, so it would be more substitute. I sort of present that Hoffman is possible with sterically, even more sterically hindered. So you saying this is Hoffman, I'm like, well, it could be Zaitsev. It's sort of just relative. Now often somebody will say, well, here we go, let's make this a more defined question. Show the Zaitsev product here. Show the Zaitsev product. That could be a question. So then you have a little more clarity in your question. But here, let's get to the problem here though. Can you make the Zaitsev product here?
No. No.
Why not?
Because it's in a ring, so your H will never be anti-coplanar. Your beta hydrogen.
Yes. That's good. Right now, is the H and the iodine cis or trans?
Cis.
They're cis. Something that's cis cannot be trans coplanar. Okay? Trans coplanar. It cannot be. First has to be trans before it can be trans coplanar. Now, when we introduced this up top, I didn't spend much time on it. Let's look at that again. Ring. Look at the bromine and the H that are anti-coplanar, also known as trans-coplanar. The arrows are pointing to them. On that ring, are they cis or trans?
They're trans.
They're trans. They have to be trans to be trans-coplanar. That right there really tells us that these cannot be trans-coplanar. But let's look at this a little bit more specifically. And let's add to that. To be trans-coplanar, the leaving group has to be axial. Look at this. Here's a boat and chair, okay? There's a chair conformation. The blue, like bromine, leaving group. And then let's call this a beta hydrogen, white. Bromine blue. Over there is the same as over here. It's symmetrical. There you go. First off, is the blue and the white coplanar? Well, let's look for a plane. Well, here's the blue right through here. The white is this way. It would have to be up like that to be planar, but I'm breaking a bond here. That's planar. It's not. It's okay. What about this hydrogen? That's also hydrogen. Is it planar to the blue? No, they're both this way compared to the plane of the blue. Is it axial or equatorial? It's equatorial. Let's do a ring flip and let's make it axial. Now let's look at the two H's. Now the white one is coplanar. Look at the plane. The blue and the white. If that's a plane of paper right through here, like the wall, they're now coplanar. They're also anti. Good to go for elimination. Let me ask you this. Here we go. Is the blue and the white cis or trans on this molecule? It's trans. Trans coplanar. Okay? Leaving group axial. Again, let's go back and do a ring flip, and let's make the leaving group equatorial. When it's equatorial, the H's over here, neither one are anticoplanar or transcoplanar. Look, neither one are. Take home. Leaving group must be axial to be coplanar to a beta hydrogen. If the leaving group is equatorial, neither beta hydrogen is coplanar. That's a secondary point. Okay, back to this. These are cis. They're not going to be coplanar. Let me just take a little bit more time and confirm it here by showing a chair conformation there. Draw a chair conformation of that. Let's put the bromine axial. Somebody told me it had to be axial to eliminate. That's what we're saying up here. It's got to be axial to eliminate. The bromine's like that. The next carbon, we're going to draw the ethyl. Should we draw the ethyl axial or equatorial?
Axial.
The ethyl is trans,
Axial.
so we should draw it how?
Straight down.
Axial, right? These are trans? Trans. The H, though, is what? This is HA. There you go. Here's the molecule. These are cis. They're cis. Are they anticoplanar? No. The alpha was anticoplanar with the bromine, not the H. And the H will never be. Will never be. What about over here, though? Let's go back over here and relabel these. Let's call this A, B, and C. They're the same, but I want to designate them because they're really different. Are they the same or different? Well, it depends on what you're looking at. Let's throw in some stereochemistry. Let's make HC bolded and make this one dashed, because that is a tetrahedral carbon. Now we see that they're a little bit different because C is cis to the iodine, but B is trans to the iodine. So let's go over here and put them. First off, axial would be straight down, right? And equatorial would be like this. Which one is this one here?
B.
Somebody said B?
Mm-hmm.
Boy? That's the trans one. Yeah, this is the trans one. These are trans, right? And that's C. There's your molecule. The bromine being axial, it has to be axial to eliminate the question.
So is that why you said earlier that when you have two hydrogens on the same carbon, you don't have to worry about the anticoplanar stuff? Because you automatically know that one of them will be anticoplanar?
Yes, one will be. Yes, that's kind of why. Let me ask this question now that we got this molecule drawn. Of the three H's, A, B, and C, which one is going to be eliminated in the beta elimination?
B.
Which one?
B.
B. This one is the only one that's anticoplanar to the bromine. Transcoplanar. The planarity here, first off, they are trans. The planarity here, it depends on how you're looking at it. If I got it on the board here, if I got the bromine, let's see. Let's just get rid of that. Wish the model was bigger. The bromine's straight up. Here's the back carbon. This is the H that's straight down. Okay, that's HA. Can y'all see?
Mm-hmm.
This is HB that I circled. That's it. Okay. In fact, let's put the ball there. Okay. There it is on the board. There's supposed to be an ethyl here down. Boom, boom. That's the only H. They're trans. The planarity here, you can't see it here, but if we turn it, and let me hold it like that, you see the planarity there? It's plain. The polarity is there. Okay. These are planar and they're trans. That's where your elimination is going to be. The triethylamine takes this H, the electrons move in here and kick off that. You're going to put double bond there. What's the product going to look like? Double bond goes there. Nothing happens down here. No chemistry, so it should be the same. There's your ethyl. Question, which H remains?
C.
HC remains. And HA is also down here if you want to draw it in. Still tetrahedral down here, that's HA, right? And this is Hoffman or Seitza? Hoffman. Why did we get Hoffman here? Not so much because this was overly sterically hindered, but it was because stereochemical requirement. The H giving the Seitza was not anticoplanar and will never be. Because this thing can't rotate like we rotated these here. Because it's in a ring, it can't rotate. Never will be. So this is another case where you actually get the less stable alkene. You get the Hoffman. Because it did not meet the stereochemical requirement. Okay, we can question.
Sorry, was that bromine supposed to be iodide?
Sorry, I can't see. Is that a, yeah, it's an iodine, sorry. I switched to bromine, same thing. Bromine, iodine, major group, you know. LG. Okay, one's at the bottom. Here's a little extension of this idea. Which reaction will be faster? What's the difference?
B.
It's just cesium hydroxide. Sodium hydroxide, potassium hydroxide, hydroxide, right? What's the difference here? Here, the T-butyl, the tert-butyl, and the leading group are cis. Here, they're trans. That looks like to be a difference. Which will be faster?
B.
Well, the beta hydrogens are here.
Yeah.
How would this group affect the beta elimination? Anybody have anything here? Let's go back to the one up top. Why did I draw the iodide? Why did I draw it axial?
It's a leaving.
In fact, why did I draw both of these axial? When it did you notice that when it eliminated over here that both groups were axial? Is that the best confirmation? It's actually the worst confirmation. Did you notice that? We call the non-hydrogens the substituents. Why both substituents axial? When equatorial is preferred, right? Isn't the equatorial the preferred conformation? We eliminated from the less preferred conformation. Or we had to. If we had drawn this equatorial, could we have eliminated? No, look at above. If it's equatorial, it will never be anticoplanar. It eliminates from the less stable conformer. Here's really how you answer this. Here it is. Which starting material, top or bottom, is more likely to exist with the iodine axial in the needed conformation? You could have answered this 2 months ago. Which one is more likely to have the iodine axial? Because the one with the iodine axial, ready to go for elimination, is the one that's going to eliminate faster. Think about it. We'll look at it next time. Or you want to do it now? Which one is more likely to exist? Well, why don't we do this? Why don't we just draw it axial, and then let's look at the T-butyl. If this is A, the T-butyl is here. How will it be if that's axial?
Equatorial.
There's cis, so this will be what?
Equatorial.
Also axial. This is A. What will B look like? Well, let's make sure the leaving group is where it needs to be. If it's axial, where will this be? This is B, which is trans, right? A was cis, this is cis, they're both up, cis. This is the needed conformation. Which one's more likely to be in this conformation?
B, because it's here.
B is more likely. Because this whole big group over here is where it wants to be. I'm happy. Actually, this group is probably going to rule the roost. It's going to be like, I'm going to be like here. Guess what, iodine? You're stuck in axial. Iodine's like, so well, I can eliminate. Over here, is this conformation going to be prevalent at equilibrium? Or is this thing going to want to do a ring flip? Going to want to do a ring flip. And when it does a ring flip, what happens to our leaving group? It goes equatorial and then game over. It can't eliminate then. B is going to eliminate faster because it's more likely to be in the right conformation that's needed for elimination. That's how you do that one. Questions? What other elimination product can be formed in reaction A? I put double bond here. That is, I eliminated this H. Could I have not eliminated one of these? Yeah. I could have also put double bond there. Now, those are both dye-substituted, so I don't know how you distinguish between Hoffman and say stuff. You need more information. They'll both be dye-substituted. I just chose to eliminate over here. There's no rationale for what we've discussed, why it would be over there versus the other one. They're both dye-substituted. Questions? Okay, so that's elimination. E1 always gets the best product possible. I'll just sort of make some summary comments about E1. It's sort of back, or it sort of just was not mentioned because we just look for the best possible product. See, E1 comes from carbocation. You make carbocation first, then you eliminate. I mean, you got 3 here. You got 3, I do 2 in here. And the weak base, such as water or something, weak base, take an H, or it can take this H. Either one, these electrons move in to make the double bond, or these electrons move in to make the double bond. There's no stereochemical requirement, because there's no leaving group. And so there's no requirement. Also, since there's no requirement, it's like your choice. Well, how are you going to decide? Well, removing this one gives the more stable alkene. So that's the one you get. Also, what about cis or trans over here, if there was? Well, you got 2 choices. Even if you had only one choice, you're still going to get the best one because this thing will just rotate and exist in the best conformer upon elimination. There's just no restrictions when you do an E1, and it all just goes towards the best. Every decision is just what's the best in terms of just regio and stereo. I won't say much more. E1 always gives the best possible alkene. It's only E2 that you've got some certain requirements and stipulations that give you something other than the most stable. Okay, from here out, we're going to look at some miscellaneous things, very important, but a little bit miscellaneous. Previous page. Is it F? Is that where we're at?
Yes.
Okay. When either substitution or elimination is possible, which will occur. For example, look at here. Well, I'll go ahead and say it. Heat favors elimination when both are possible. Look at these examples. If you take this substrate and just heat it with water, we can show an E1 product. Plus HBr is eliminated, and then water. Really, water didn't do anything. You could show this as H3O plus if you wanted that to act as a base. That would be elimination by E1 mechanism. On the other hand, we can do the same reaction and get a substitution. This will be an SN1 product. Look at the difference in entropy. If you ignore water up here, which is no change, 1 molecule going to 2. That's a favor in entropy. Down here, where water is involved because it acts as the nucleophile, 2 molecules going to 2. Is that a favor in entropy? No, there's no favor there. When you eliminate, you produce another molecule. Entropy is good. And in our free energy equation, temperature magnifies entropy, right? So if entropy is good, how do you make it better overall? Temperature makes it better overall. So heating is going to magnify entropy. reaction, heating the elimination reaction, well, heating any reaction is going to favor the elimination pathway because it's magnifying entropy. Look back through that. That's when you have a choice, because such a reaction here has a choice. It could do an E1 or an SN1. I'm not sure how we got from F to number 2. We have to see what category we were under F. Okay, you can look back at that. Number 2, involvement of a good nucleophile will favor substitution. While a poor nucleophile will favor elimination. Look at these examples. If you take this alcohol with HBr, you're typically going to get a substitution product. Sort of just like the shaken, not stirred lab. Okay? But if you do this with HF, it will more likely give the elimination product by an E1 mechanism. Why? What's the difference? Br minus versus F minus. Br minus is a better nucleophile. We stated that earlier. Better nucleophiles will favor substitution products. They will act as nucleophiles. F minus is a worse nucleophile, tend to favor elimination. F minus is also a better base, so F minus prefers to act like a base and take an H. We can apply this to a common reaction here. This is a common reaction of alcohols. Treat them with an acid. This would be a catalyst in this case. And eliminate to make the alkene. We're eliminating water here. Okay? We can show that like minus H2O. Or if you want to come over here, you can say this plus water. The water is eliminated from the reactor. This is one way to show that. Because we're removing an H here. Okay, we're removing water, putting in the double bond. Obviously, elimination. Is it E1 or E2?
E1.
Yeah, it's obviously an E1 elimination. How do we know it's E1 and not E2?
Poor
That's a good statement. How do you know that? Oh, you're just reading to me. Why is it not E2?
Not very strong base. E2 requires a strong base.
Do what?
E2 requires a strong base.
E2 requires a strong base because it's a concerted, the base acts as a pulley. Okay. Do we have a strong base?
No.
We're doing this with in sulfuric acid. There ain't no strong bases in sulfuric acid. What if we used a strong base? Could this eliminate by E2? Strongest base you could think of. What if we reacted this with the strongest base? Could that do an E2 elimination?
No, because an alcohol is reprotonated.
Is that a good leaving group?
No.
No. How do you make it a good, better leaving group?
Make it more.
Protonated with acid. You can't have a strong base and acid together. This cannot do an E2 elimination. Yes, alcohols cannot eliminate by E2 because E2 requires, that would mean you have to have a strong acid to make it a good leaving group and a strong base to make it eliminate. Those aren't compatible. This is an E1. Since it's an E1, what's the first step of this? Think through the mechanism. What's the first step?
Protein.
Protonate the oxygen, make it a good leaving group. What's next?
Leaving good leaves.
Just leaves. That's your unimolecular pathway, either SN1 or E1. Make cation, right? Then what's the final step? We've got HSO4 minus. Okay, we said good nucleophiles will attack and give you substitution. Is this a good nucleophile? No, never use it as a nucleophile for anything. Never a nucleophile. But it will act as a base, or you can use water. But if it acts as a base, and I usually show this generically, it takes the H, these electrons move in, you get your double bond, the water formed right there. There's your minus water. But what are we reforming here? Right? We reform our catalyst when the sulfate, bisulfate, takes the H. It's a common reaction of alcohols to dehydrate them with strong acid by an E1 mechanism. It goes E1 largely because this is a bad nucleophile. It will never attack the cation. It will only eliminate. Just like HF. F will never attack the cation. It will only eliminate. Bad nucleophiles. Br minus is a good nucleophile. Okay? If you do the same reaction with HI, you're more likely to get the substitution product, where the iodide I minus will add here, give you the substitution product instead of the elimination product. Okay, number 3. We really already said this. Let's just confirm it. A more sterically hindered base will favor elimination over substitution. Let's approach it this way. Which base is best for this reaction of the 3 given?
The last one.
Which base is best?
Last one.
Last one. Why?
Sterically hindered.
Sterically hindered. What does that do? Why not use ammonia? Ammonia is a base. I mean, what are we looking to do? These are all strong bases, so it would be E2, right? I mean, why not ammonia do it? What can ammonia do instead? See, this could do substitution as well. This could do substitution as well. Why does this not like to do substitution? Sterically hindered makes it prefer elimination. And if you want elimination, then this would be it. Right? Do we have to worry about getting a Hoffman versus Sasef in this example?
No,
Why not?
because there is no, that's only one alpha hydrogen.
There's only one beta carbon, beta. There's only one beta carbon.
Yeah.
There's only one.
Mhm.
And does the alkene we generate have any stereochemistry?
No.
No. So that's the only product possible. We've kind of already stated that, but that's just there. What's next? Clever ways to make ionization of a halide to a carbocation easier. We haven't done this before. Something like bromine is a good leaving group. We don't need to activate it like we do in alcohol. But sometimes you may want to. Clever way to activate this is to use a Lewis acid. Not a proton acid, a Lewis acid. A common Lewis acid is silver ion. By the way, what's the definition of a Lewis acid? Lewis acid accepts a lone pair, right? Right? Silver ion can accept a lone pair. Now this is a little vague of how this actually happens. I don't really want to show don't really want to show that, but maybe I'll go ahead since I did. This is a lot like an OH being protonated with H+. Okay. You just don't, we made the bromine positive. We typically don't do this with H+. With halides, you can use silver plus. And we could show something like this. Now that the bromine's positive, now it's really going to want to leave. Because now if it leaves, we get our carbocation that we're looking to get, plus what? Plus silver bromide. And silver bromide will precipitate. And the precipitation sort of drives the reaction. And have we used silver before? Yes. So you can do this reaction here. You can look at the outcome. Here's your silver bromide precipitate. You can also use this. We'll finish up here. We'll look at it on your own. We'll begin next time. We can also use the silver as a chemical test. Look at that. We'll pick up there. Chemical test. We'll finish up this handout on Friday. We'll have a quiz on Friday over elimination reactions and some substitution. We'll meet upstairs in lab this week. Have a good day, guys.